Okay, let us proceed to the seminar part, to the part of practical tasks. And if I remember well, the first task was to describe the center, the Poisson center of GL2. So we consider just the polynomials generated by by the element of the Lie algebra GL2. It is 4-dimensional space, 4 generators, and we consider all polynomials on 4 generators. And we found it a central element of the first degree. So first of all, we understood that the problem of describing the center can be reduced to the homogeneous parts of the center. So we can separately treat the homogeneous parts of the central elements. So if we have some central element, its homogeneous parts are also central elements. This was the statement. And this simplifies the task of searching all central elements. We consider it the central element of the first degree, E11 plus E22. It is in S1 of GL2. Okay, let us describe the central element in the C2 in S2 of GL2. So we are interested in homogeneous polynomials of second degree, which are central in our Poisson algebra. Do you understand that the description of the center could be reduced to the study of homogeneous parts?
Yes.
Yes. So if it exists a homogeneous element of degree 2, which is central, how to find it? So my proposition was just to consider the indeterminate coefficient and to consider all homogeneous second degree elements. What do you think? Do you understand what is the homogeneous second degree element in this algebra?
No, sir, I don't understand what is the second degree homogeneous element in the S2GL2.
You see, our algebra is just the polynomial algebra with generators 1, 1, E12, E21, E22. So it's just a ring of polynomials on four generators, 4 letters. In such a ring, there is a grading, which is just defined by the degree of monomials. If we are interested in functions of degree 2. We are looking for central element as function of degree 2. Is it clear or not?
Can we just select two of the generators as the degree 2 generators? Then we make the combination of these degree 2.
Yes.
Generators, and we make some coefficient of it, and we solve the Poisson bracket and find the relationship between these coefficients.
Yes, exactly. But how to find them all? So I know, for example, that C1 square is a polynomial of degree 2, and it is central, because C1 is central. Okay? So the polynomial E11 plus E22 square which is E11 square plus E22 square plus 2 E11 E22, it is obviously central.
Just because all have degree 2.
Because all have degree 2, and because it's a square of the central element. The product of two central elements will be also central element. Else due to the Jacobi identity. So this element is central. But I know another element.
There's some more, I think.
C21 is the following one. E11 E22 minus E12 E21. I know that this element is also a central element.
From where? Last time we checked, we haven't checked it, I think.
You checked this, I suppose.
Okay. But I think last time we checked, everything was like degree 1. Well, my idea was to write all the possible polynomials of degree 2, monomials of degree 2,
Uh-huh.
and then check write the Poisson structure and use, we had a formula last time, the way we checked.
Did you check this?
I think no.
Let's make it now. John Long, would you like to check that this element is central?
Yes, of course, Professor. Yes.
Could you demonstrate your screen?
Yes. Okay, so these are the Poisson brackets. So we have tried this E11, E22 minus E12, E21 with E11, E12,
Uh-huh.
E21 and E22 and all of the Poisson bracket we get 0. So this is a center element. This is a center.
Very good. Uh-huh.
Okay, so it's done.
Very good.
So that's
Please
yeah.
look and see. Thank you very much. Let us try to demonstrate that there are no other element of the second degree. So, lemma. Each C from S2 and GL2 is a linear combination of this one. Alpha and beta, such C is alpha E11 plus E22 square plus beta E11 E22 minus E12 E21. That is true. And how to demonstrate it? Do you remember the Lux operator in this case? E11, E12, E21, E22. And two such elements can be interpreted as the spectral invariance of this Lux operator. C20 is the trace of L square, and C21 is the determinant of L.
You know, that's why we don't know, so we have to check maybe.
No, it's just
Okay.
declaration that such an elements which we know to be central are spectral invariants of this Lux operator, of this matrix composed with the help of generators of our Poisson algebra. Okay, there is a very important property of our Poisson algebra. Let me formulate it as also as a lemma. That when we consider the Poisson bracket of monomials in our Poisson algebra, just with the diagonal generators of diagonal matrix, E, I with a monomial, it is also some constant multiplied by a monomial. Some constant which depends on I and M is constant R. Have you understood the statement? John Long, is it clear the statement of the last lemma?
Not very clear, sorry.
You see, here is any monomial in our algebra, so it's monomial function. Okay?
Yes.
For example, this monomial or this monomial, but not the sum. So it's a monomial. M is a monomial. Then the Poisson bracket of each diagonal element with a monomial, it's the same monomial multiplied by some number. You see? It's a very strong property.
I understand.
Okay?
I understand.
Okay. Why it's true? It's better to demonstrate by induction. If a monomial M is a product of two monomials, and if the statement is true for the monomials of the lower order, you understand? Then by the Leibniz rule, EII with M1 multiplied by M2 is EII. I'm sorry. Yes, EII M1 multiplied by M2 plus M1 multiplied by EII Poisson bracket with M2. And if this, if our hypothesis is true for the monomial of the lower order, then it is the same as he I M1 M1 M2 plus M1 he I M2 M2, and it is the same as he I M1 plus he I M2 both multiplied by M1 M2, and it is the same as he I M1 he I M2 multiplied by M. Okay? So if the statement is true for the monomials of the lower order, this one and this one, then it is true for the product. And it is true as a base of the induction, we can consider the just the linear generators, and the statement is true for the linear generators. Okay? It allows to make some condition on monomials in the central elements. You see, if now let C is the sum of monomials. A sum of monomials and C is an element of the centrum center of our algebra. Then Mi commute with EJJ separately. You see? So if the sum of monomials commute with diagonal elements, each monomial commute with the diagonal elements. Because the commutation with diagonal elements act on each monomial separately, multiply by function by number.
But here in this lemma, we say like the commutator of each monomial with the diagonal element is just that monomial.
You see, if this is a centrum, then this is equal to 0. But this commutator is the sum over I, he, j, mi multiplied by mi. And this is equal to 0. And these monomials are linearly independent.
So, in short, we have the sum of all possible monomials and all individual monomials that commute with the diagonal elements.
Yes. Because the commutator with the diagonal elements doesn't merge, не перемешивает, doesn't merge the monomials of different type. Okay. So these monomials are linearly independent, and that's why each summand is 0. For all I. But the commutator of a monomial with the diagonal element, it is very simple to calculate. What are the monomials mi als n s2 gl2 commuting with EII. Maybe it is simple to just to calculate. So E1 square, E2 square, E1 1 E2 E1 2 E2 1. I'd like to say that all odd monomials doesn't commute. But what are other monomials? E1 2 E1 1 E1 2 E2 2 E2 1 E1 1 E2 1 E2 2.
Yeah, then
It's okay. No, it's not okay.
how can we like understand instantly? Can we?
Yes, let us understand this. So when we calculate the Poisson bracket of such elements with the diagonal elements, so we can take in mind that the diagonal elements commute between themselves. Okay? But for each diagonal element, there is a linear non-diagonal element which doesn't commute with it. And it is even true for every rank n of the Lie algebra J-Ln. So then we calculate this E12, E11 with E11. We get only non-trivial commutator here, and it is minus E12, E11.
So you just like take commutator 2 times
And use that E11 with E11 is 0.
0.
Mm-hmm. So we calculate this Poisson bracket by the Leibniz rule, applying this differentiation to this element and to this element. But with this element, it's trivial. So the only non-trivial part is here, and it is really non-trivial. So it is minus E12 multiplied by E11, this one. So there is a more general argument in this case, but it's a little bit demanding, technically demanding. So it's related with the Lie algebra J-Ln. It's a joint action, the character of this action. But we can apply it just directly in this case. So we see that the only monomials we have to consider are linear combination of these monomials. The next step, I suppose, we have to consider just the general expression. So x e11 square plus y e22 square plus z e11 e22 plus w e12 e21, and to consider 4 commutators.
Then find this xy.
Yes, there will be some conditions on x, y, z, and w. So I know the answer, but you can find. So this argument restricts the dimension of the space of possible solutions. It's better to solve the system on 4 variables than on 8 variables.
So how can we find this coefficient? We just like commute every monomials with the central element E11
Yeah.
and E22 maybe also.
For example, then we calculate this commutator with E11. What we obtain? Would you like?
Yeah, maybe. So, let's calculate it. X. So
You see, it's 0.
yeah. So 1 is 0.
Uh-huh. Mm-hmm.
So you get something like this. Let me just. So it will give you 0 overall. Yes. So it's 0.
Mm-hmm. The same is here, because they commute.
Yes.
Uh-huh.
So you just have only this guy.
Uh-huh.
That L E E11 E22 E11 like this. So what it will be?
Else is 0.
Just because this
Yeah.
this. And here here it will be not 0.
It is 0, but for less evident reasons.
Then we need to check, I think. E11 E21 E11, right?
E12.
We can calculate. So this plus
1, 2.
Yes.
Mm-hmm.
And then what this is? I forgot.
2, 1.
E12, E21,
Mhm.
right? Something
Mhm.
like this. Plus E21. Here is E12.
Minus E1, 2.
Yes. So it should be minus here.
Mm-hmm.
So if we sub, they cancel out.
Yeah.
So, yes.
So there is no conditions
Okay.
from this commutator.
And then we need to
1, 2. I think the 1, 2 will be non-trivial.
yes.
You imagine that the commutator with 2, 2 will be also trivial.
Same, yes,
Uh-huh.
yes.
Mhm.
Square E12, for example.
Mhm.
Maybe I can quickly calculate everything.
Please. Yeah.
So what was that formula with two indices?
With indices.
Help me to calculate it quickly.
Mhm. Maybe you remember how you multiply matrices.
Yes.
Firstly, you verify
Yeah,
if
yeah,
these
yeah.
indices coincide. So it is EAL multiplied by delta JK. And minus the multiplication in inverse order. So
Yes.
you verify that these indices coincide, delta EL, multiplied by EKJ.
Yes.
Okay?
Seems like I spent a lot of time on that. But plus the same thing. So there will be appears 2 times. So I write here 2 times this. And it will give me JK. They represent, it means like 1, 2, right?
Mhm.
This is 1, 2. So 2 alpha it's E11, E12, something like that. So now the next one is eta.
I'm sorry, it is alpha?
Yes.
Why? X is a coefficient here. No, it's a Poisson bracket.
Okay.
The coefficient is X. So you see here is the linear
Yes,
combination.
yes,
Uh-huh.
yes. And then you put eta as a coefficient.
As you like, yes. It was just Y, X, Y, Z, and W.
What it will give me? It will give me y. This and this will coincide. It means I and L. So it's kg. Kg is 1, 2. Y into 2, E1, and minus. Plus Z E11, E12, E22 with E12.
Mhm.
Jet E11, E12, E22 plus E11. So this coincide. So to make jet E12.
Mhm.
E22 plus E2. So it will be like 1, 2 and the minus.
1, 1.
Yes. So got another term over here, and he 1 to 2 1, right?
Yeah. Here, do you need 2 due to this?
Yes, exactly.
Minus y, minus 2y.
Yes.
Mhm.
And it's with 1, 2. So we can calculate very quickly. This will give me E22
Mhm.
and 0.
0, but the commutator of this is a difference of C22 minus C11. The commutator.
Okay. So it's like this thing. E22 minus E12, E11, right?
Mhm.
Yes.
Uh-huh.
So got another. And the last one, or it's the last one. So we need to find this x, y, z, w. Okay, what other condition we have over here? So this whole sum is actually equal to
You see, for example, x should be equal y. Y.
just because we have to cancel these two guys.
But why we have to cancel them?
Well, at the end we need to get 0, isn't it?
Because you see here expression of the same type. It's a sum of the same
These
monomial,
two things, yes.
and here else.
Mm-hmm.
So in to these cases,
in these two cases,
yes.
This J and W will be also
with the same coefficients.
Same coefficient. So maybe we can put everything 1.
For example, but necessarily x is equal to y. If not, it is not 0.
Okay. So then we can say like everything is 1, x, y, z.
So you see, it is the first condition,
Mm-hmm.
but we need to find the second condition.
So we need to contract with another.
Yes, possibly we need to.
With maybe to 1.
Okay.
Okay. It's a lot of work.
Just a moment. Just let to see. No. Look, another condition. So x is equal to y, and the second condition is that 2x is equal to what? Z plus w. It's the second condition.
One. Yes.
make a calculations on without mistakes, it's better to write it in a basis. So just to compose the similar monomials. You see, the monomials are of two kinds. This monomial and this monomial. It's better just to write a coefficient between at each monomial. Do you understand?
Yes, so you're saying like here, put it here to understand it correctly.
Yes, just to write. You see, there is a monomial of this type and the monomial of this type. We need to write the coefficient at each monomial.
Yeah. So it has coefficient like z over here.
Yes.
And here is w plus this, right? And here you have like minus z, and here you have plus w. Minus w.
Minus w. And then?
Then we already figured it out, but okay. So 1, 2, 2, 2 is this, so it's like minus 2y. And here 1, 1, 1, 2 is plus 2x.
Plus 2x. It should be 0.
Yes, and this should be 0, yes. So it says that x jet so if we solve this, it will give me what? These guys will cancel out. We will have this only.
It's a system of linear equation. There are two equations and 4 variables. Okay? There is a two-dimensional space of solutions. You see? We need a two-dimensional space of solutions.
We need 2 more equations.
No. It's done. It's done. The space of solutions is two-dimensional.
Okay.
We have to understand that it is exactly the linear space generated by two quadratic Casimir elements. How to describe the space of solutions? For example, by basis of solutions.
What do you mean basis of solution? It means like this.
Two independent solutions of this system of equations.
Well, first of all, we see that x should be equal to y, and z should be equal to this w.
It's one
solution.
Please write it.
So I'm saying that
if not, a risk to make a mistake.
I'm saying that x should be equal to y, right? And here. And
you see, it defines a two-dimensional space. Okay.
Two-dimensional space by
in the space of 4 variables x, y, z, w. It's a 4-dimensional space. In this 4-dimensional space, the system of equation defines a two-dimensional subspace.
Okay.
It's sufficient to find a basis in this subspace. Just 2 vectors, 2 independent vectors in this space of solutions.
Well, what is vector we have here?
Just a set of indices. For example, x, y, z, w. 1, 1, 0, 0. Is it a solution?
I think yes.
Yes. 0, 0, 1, minus 1. Is it a solution?
I think no. If you put x
this is not solution. We should 1, 1.
But the second one is not a
Solution, zw. z 1, minus 1, 0. Minus 1, 1, 0.
Okay.
You see? This is 2 independent solutions of this system of linear equations. They constitute a basis in this space. Each solution can be decomposed into the linear sum of such. Okay? What is this?
So this is so we can write it.
Just to write this linear combination in these terms.
Yes. Yeah, I understand what you want from me. So just writing.
Mm-hmm.
The thing that you wrote in the beginning.
But with minus. You see,
Yes.
it's 1 minus 1. Because we should place here 1 minus 1
Yes,
and 0.
cancel.
Uh-huh. And this is a determinant, you see?
Yes, and this is just that.
No. There is some subtlety here. What is the trace of L square is E11 plus E22 square plus what? 2 E11 to 2.
Yes, but we have something different over here.
Yes, let us add 1 1 plus E11 E22 and minus 1 1 E22. Then this is the trace, and this is minus determinant.
So crest minus determinant.
Yeah.
Crest square minus determinant.
Mm-hmm.
Square minus determinant.
Uh-huh. And what is the vector corresponding to just the square of trace?
You have already written this.
In these
here,
terms, yeah.
In these terms,
Yeah.
So
Just a vector. Uh-huh.
So look like 1 1 2 maybe.
1 1 2 0.
Because
Okay.
the last in is
Uh-huh.
absent over here.
Is it a solution of this system? It is x, y, z, w. Is it a solution of this system?
If we put x equal to 1, it will be like 2. So 2 and w is 0 minus 2.
2, 0, 1.
Not a solution.
Solution? Y is 1 minus
Yeah, there is 2.
I see.
Yes.
Yeah.
Yes. This is also the same.
Uh-huh.
2
2, 0,
minus
1.
yes.
It's a solution. And we need to verify that two such solutions, this is the determinant and this is the square root trace, that these are linearly independent. Are these vectors linear independent? They are not collinear.
Seems like they are linearly independent.
They are linearly independent. If not, they should be collinear, just proportional. They are not proportional. It means that they are linearly independent and their solution to the system of equations, it means that they form the basis of the solutions, of the space of solutions.
Okay, so
And each such element should be represented as the linear combination of such solutions. You see?
so the moral of what you're trying to say is this and this guy are the basic
Generators, yes.
generators.
They generate all the central in the degree 2.
Yes.
But we have demonstrated it because we found the complete system of equations on all monomials, on all homogeneous polynomials.
Okay. Okay. So finally, the generator of solutions, right?
Yeah.
Generator of solution is just the trace L square and determinant L.
Yeah. Very good, thank you very much. To demonstrate the same statement in higher degrees is a little bit complicated, more complicated. I'd like to propose to you a more efficient technique, but to do it we need to solve another home task about the Hamiltonian vector fields with linear Hamiltonian functions. Do you remember? Do you remember the next home task? We will return to this, but after solving the second task.
May I ask a question? That when we defined Casimir function, we said all the smooth function, but we verified all the base function instead of the smooth function. I mean, there are some function not in polynomial form.
Yes, it's an important question, but sometimes it's sufficient to work with polynomials, just with a series. So my statement is about polynomials in this case. So you see, it is also important to describe all the polynomial central functions. And there is a very strong statement that the center of this Poisson algebra is also a polynomial algebra, and one could construct the set of generators of this polynomial algebra. But the task 2 was the following. We else consider our space, our Poisson manifold, which is the dual space to our Lie algebra. In our case, it is GL2 R dual space. The algebra of polynomial function itself is the symmetric algebra of GL2. And we consider now Hamiltonian vector fields. Hamiltonian vector fields for functions h which are just linear function. So let us consider Hamiltonian vector field on our Poisson manifold with a Hamiltonian, which is just a linear function. It's just a generator of the Lie algebra. What could you say about this Hamiltonian vector field? Could you solve it? Could you define the dynamics along this?
Yeah, maybe if we have the Hamiltonian, we can.
And it will help us to describe the center. Because the central functions, the Casimir functions, they are preserved along Hamiltonian vector fields. They are constant along the trajectories of Hamiltonian vector fields. Is it clear?
Yeah, just because they are centered.
Because they commute with Hamiltonians. Because they are integrals of all Hamiltonian vector fields. Okay? They are stable along vector fields.
Mm-hmm.
So if you if you will succeed to describe the Hamiltonian dynamics along the Hamiltonian vector fields with linear Hamiltonian functions, it will allow you to describe the center.
So we have to find the equation of motion of this system for the following Hamiltonian.
Yes, we just consider this four-dimensional space. It is our space, which is R4. Okay. On R4, we define the Hamiltonian vector field for H, just the basic function, basic linear function. But it's a Hamiltonian vector field. We can solve it. First of all, we can formulate it and then find the trajectory. If we will successful, we can describe these trajectories and characterize the integrals along all trajectories. But in this case, it has a very simple geometrical interpretation. So it will give us an idea how to describe the center.
Could we just use that the factor act on some EIJs, just the coordinate of it? I mean, the bracket of it.
Yes.
That's how we defined it.
Just how to define the Lie Poisson structure?
Yes.
Uh,
I mean, when, for example, you use EIJ and another, and this is the coordinate of it. Yes.
So the Poisson bracket on linear functions is the same as the Lie algebra structure, as the Lie algebra commutator. So it is defined by the same formulas.
Yes, and it is also the coordinate.
Yes, exactly. Very good observation.
What is coordinate? This EIJs?
Yes, they are linear coordinate,
Okay.
but we can consider them as functions, and to consider the Hamiltonian vector fields.
As a sum of all them?
But just for each coordinate function, we can consider its Hamiltonian vector field.
Okay.
And to understand how it acts, you see, x Eij, we can apply it to the function EKL. It is the Poisson bracket of the function h with this function, and if both are linear function, it is the same as the commutator in the Lie algebra.
Yeah, okay, but how it helps us to solve the task? Or this is the task?
Now we have to, what to do? We have to solve the equation. EKL dot is equal to Eij EKL. But you see, it means the point, when point goes along the Hamiltonian dynamics, the function, so the point is in G star. And this is the function which depends on this point. And this function satisfies such an equation. Now we have to solve it.
And find
The trajectories. So we have to find what? We have to define P of t such that d over dt of EKL of P of t is equal to Eij of P of t, EKL of P of t.
so this P is a trajectory.
Yes, P is also a matrix if you want. So in our case, we can identify GL2 square, the dual space can be identified with GL2 with the help of the form trace of A. So you see on the space of matrices there is such a bilinear form. Okay, and it allows to identify the dual space with the space itself, and it allows to think on the dual space also as a space of matrices for 2 by 2. I'd like to rewrite this EKL P of t okay. You see this this bilinear form is invariant with respect to the action with the commutator, and it can be written as Eij. Okay, I prefer to invert it, to write it EKL Eij P of t Eij with minus. And it means that, so the derivative acts just on P. It is equivalent with the fact that d over dt of pt is equal to Eij with pt. Please see. Minus, I'm sorry, minus. So if we interpret this point in the dual space L as a matrix, we can describe its trajectory along the vector field Eij as a solution of such an equation. Do you know how to solve this equation if P is a matrix?
If E is a matrix?
If P is a matrix. So if the derivative is a commutator with some matrix, some constant matrix, how to solve this equation? So in fact it is related with the exponential map in Lie algebras. And it obviously will be mentioned and described in your course on Lie algebras. But the solution in this case is the following: P of t is P of 0, with the conjugate action of the exponential of t Eij E minus t Eij.
Something we have seen in quantum mechanics, I think.
But maybe with minus, like this. So if you don't know such an answer, it is a task to verify that such a trajectory solves this equation. So the task is that one solves two. We will use a lot such a technique, such calculations. But now, if we suppose that if you suppose you do this task, let us return to the question of Casimir elements. The Casimir elements are functions which are stable along all trajectories of this type. So they are preserved by the joint action of each element in our group.
Okay.
What are such functions?
It's a function that preserved by the action of
A joint action of the group by conjugation. So you see, P is a matrix. Hamiltonian vector fields given by linear functions acts as conjugation of some group elements on matrix P. And we are looking for function on P which are preserved by conjugation. In fact, by conjugation of a generic group element, because such one parametric subgroups in our Lie group, they generate all the group. It is also a peculiar question.
Obvious thing, maybe.
Yes.
Could we use the diagonalization that
Yeah.
we do for P0 and problem is when you do the diagonalization is could be in the form could be that also orthogonal thing into the exponential thing. I mean.
No, it's not related by the scalar product. It's a general question in the linear group. So you have just GLN, not orthogonal matrices. Q says that it is related with the diagonalization of pi. It's true. Of P. It's true. But I'd like to formulate this fact in a more general way. So, let us write something. First of all, claim. Pi of t, which is e minus t eij pi of 0 t eij is a trajectory of x eij passing through P0.
Yes, from the definition.
A Casimir function is an integral of each Hamiltonian vector field. Okay. It means that the Casimir function, so it's C, it's a function on P. And it should be constant along each such trajectory. So it should be the same for P of t, C of e minus t eij, P of 0 e t e j, and for all I and j. Okay? it means that C of P should be equal C A minus 1 PA for all A in GL2. Here it's notation for the group. So for the space of invertible matrices 2 by 2, P is just a matrix 2 by 2, A is an invertible matrix 2 by 2. How to describe all such functions? Do you know?
So what did you write from this line, this C, yes?
Because such, so you see for a fixed I and
just like denote A as this thing, right?
yes, but I go further. So here there is a one-dimensional, one-parametric subgroup of the Lie group GLN. You see the elements of this type, they form a one-dimensional subgroup. If we compose the element of this type, E T G multiplied by E S E I J, it is just E T plus S E I J.
Yes.
It's a commutative one-dimensional group. But so it's quite also important property that the subgroups of this type for different I and J, they generate all the group GLN. So just composing different elements of the subgroups, you can find all elements of the Lie group GLN. And it means that you can, here you can put any element of GL2. So the answer to this question is the following, that the space of polynomial invariant functions is generated by the coefficients of the characteristic polynomial. By the coefficients of the characteristic polynomial of P of lambda, which is determinant of P minus lambda E. You know.
Yes, I think I know.
That the coefficients of the characteristic polynomials are invariant functions, and they generate the ring of all polynomial invariant functions. You see?
That's the answer.
Huh?
That's the answer.
Yes, that's the answer. Yes, because in our case we have found the basis of the invariant polynomials. It's the trace and the determinant. The only two coefficients of the characteristic
I
polynomial.
think such task we had in the course of analytical mechanics.
It's a very general question.
It was a physical task, so it was like solving some equations.
Yes. You see how different subjects interact in our course. So with dynamical Hamiltonian vector fields, they act exactly as the conjugations, and it means that the Casimir functions are just invariant functions. Okay? Okay, let us briefly discuss the third task. It was about the Casimir functions of the standard Poisson structure. You see, it is R2n standard Poisson structure structure. The question is the center of what is the answer?
Only constant.
Yeah. Just R. Only constant. So the constant always lie in the center, but in this situation there are only constant. There are no other functions. But how to illustrate this? This is true, but how to illustrate it?
Is the same to require the grad in all the direction be 0?
Could you write it to show to other students and to me? Okay, I can write it now, but please be ready to participate the seminar part next time. So in this situation, suppose that C is a central function. With our Poisson bracket given by the standard Poisson bivector. Then C with pi I is equal to minus dc over dqi. And this is 0 because C is central. And C with qi, it is equal dc over dpi. And this also should be 0. So it's a function with all first derivative with all trivial first derivatives. It means that it is constant. Is a constant function. So you see the standard Poisson structure has not central elements. It has not the structure of foliation into symplectic leaves. And okay, we will discuss it next time. So we will discuss what is the symplectic leaf. So in the standard situation, the only symplectic leaf is the whole space, and we know that the space is symplectic. So the Poisson bivector is invertible in this case, and the inverse matrix produces symplectic form. We stop for today. Good continuation, and see you next week.